All right, so we are now moving into the chapter 19 problems. I've decided problem 5 I'm not going to talk about just because basically I think you can look that up in the answers, and in the answers they give you a brief explanation that's pretty good. So I think I would just basically be reiterating what you have there. Okay, so let's move along instead to number 11. And in number 11, they say we're asking people if they believe in ghosts. And we have this many people say that they do, this proportion. And it's a sample in which n is this many adults that they asked. And find the margin of error if we want 90% confidence in our estimate. Okay, so margin of error is going to equal some special z value, some critical value, times the standard error. And the standard error is going to be p hat times q hat over n, and it's going to be the radical of all of that. So in this case, the the critical value is like 1.645. It's 1.65, and I'm going to put 1. I looked it up and I got this. Okay, and underneath I've got my p hat, I've got my q hat, which is 0.62, and my n is this. So I calculate all this, and well, you can get it, and you can see what that comes out to and check it against the back of the book. But this is how you would set it up. Okay, so that's basically all we have to do for A. Now B, it says explain what that margin of error means. That means that the value we get from this, right, we are 90% confident that the actual proportion in the population, the number of adults or the proportion of adults, not out of this sample, but out of the population from which that sample was drawn, right? We don't know if it's exactly 38%, but we are 90% confident that it is 38% plus or minus that margin of error. So let's say that margin of error comes out to be, let's say this comes out to be like 5%. Well, then this would be 38% plus or minus 5%, so it would be from 33 to 43%. Then we'd be 90% confident that it's between 33% and 43%. So that's what that means. Okay, so part C, if we want to be 99% confident, will the margin of error be larger or smaller? Well, actually, it will be much larger, and that makes sense. So let me erase this. My critical value will be different. That was the critical value for 90% that I'm erasing there. The critical value for 99% is something bigger, 2.33 approximately. So think about that. If we want to be 90% confident, right, we can draw the lines here, right? But if we want to be more confident, we got to draw the lines out here, right? I mean, if you're 99% confident or something, you're really going about something, then you're really going out on a limb, right? Well, you can't go out on a limb about something really specific, like just like the middle, like that. You got to draw it all the way to the ends if you want to be 99% confident. Okay. So, and then it says find that margin of error. Well, once again, you can go ahead and multiply. It'll be the same product, except we have this critical value instead of the other one that we had before. Check your answer in the back. Okay, and then finally we have, in general, if all other aspects of the situation remain the same, will smaller margins of error involve greater or less confidence in the interval? Well, we basically already said that. You get a smaller margin of error, that means you're talking about getting tighter into the middle here, with your smaller margin of error. Well, the more specific, the more tighter you get in there, the more specific you're being about what you're predicting. So if you make a really specific prediction, you can't be very confident about it, or not as confident about it, right? All the way down to a confidence of 0 if you were talking about one particular number, right? You think that your proportion is going to be exactly 0.38. Well, you can't be any more than 0% confident that it would be exactly 0.38. All right, no matter how big your sample is, you can't be, confident about a very specific value, only about an interval. Okay, so let's pause. Okay, so moving on to teenage drivers here. Number 13, so we've got 9 out of 582 accidents, 91 of them teenagers are at the wheel. So our proportion is 91 divided by 582, and so p hat is, what is p hat then? So we've got 91 divided by 582, which is about 0.156. Sometimes I'll work it out for you, and sometimes I'll just have you do it, because you can, if I'm saying what it is, you can just do it. So we want a 95% confidence interval for the percentage of all auto accidents that involve teenage drivers. So that means we got to do the margin of error, which is going to be 95% confidence. That's my critical value. Here's my standard error. Times 0.844 over 582. Okay. So you do all that and you get the margin of error is, I think, this much. And so we're talking about an interval from about here to here. We're 95% confident that the true proportion of teenage drivers is between 0.127 and 0.186. So we just explained what our interval means for part B. We're 95% confident that the true number is between those, not just out of our sample, but out of all accidents, maybe in the city or the country or whatever, wherever the insurance company covers. Okay, so C, explain what 95% confidence means. Now, this was a distinction that actually made a huge difference on the example of an AP free response question that we tried. They were asking us to interpret and explain, what does 95% confidence mean, right? As opposed to part B, which is a different question, apparently, explain what your interval means. Now we're saying, what does 95% confidence mean? So that what it means is that in the long run, if we take many samples of this size, right, and we make confidence intervals that are all 95%, so basically if we do this a whole bunch of times, in the long run, 95% of those intervals will contain the true value of P. That's what 95% confidence means. So for part D, a politician urging tighter restrictions on driver's licenses issued to teens says in one of every 5 auto accidents, a teenager is behind the wheel. Does your confidence interval support or contradict this? Well, 1 in 5 would be 0.2, right? That would be the value of P if that were true. It's outside of our confidence interval, and this right here is 95%, right? And this is significantly more than the upper bound, actually. This right here is significantly more than the upper bound of our interval, right? So we can say that the probability that this is actually it is something less than 2.5%. So let me explain. If this is 95%, right, that means we have 5% left over, half of it's here, and half of it's over here, right? So 0.2 is somewhere in that upper 2.5%, and you know what? It's pretty high up in that upper. So we could say that it's even less significant than 2.5% is the chance that this would be true. So ordinarily what we would say at this point is we reject the idea that this is the actual proportion. We reject it based on our confidence interval. Okay, so I'm moving on now to number, where are we? Number 29 we're going to do. Okay. Now we're making a 90% confidence interval, so I'm just going to write this right off the bat. I can do 1.645 or 1.65. For the percentage of deer that may carry the ticks, this was a sample of 153. 32 were carrying ticks. So that means my p hat is 32 over 153. So that's 0.209. Okay. And here's my margin of error. Here it comes. 0.209. Okay, now let me get a good, hold on folks, let's do this right. 0.209 times, let me just explain what I'm doing here. I made a homemade stylus out of a plastic tube of a pen and a Q-tip with water on it and aluminum foil, right? Because I realized that I could use this to maybe try to write on the screen, and I'm having, you know, mixed results, obviously. But it's taking too long to try to write all this with a mouse, and so this is desperation here. See, if I do it with authority, it actually works. Okay, so, and we have a sample of 153. Okay, so I'm gonna go ahead and punch all that in. 0.209 times 0.791 divided by 153 square root times 1.56. So I get 0.054 approximately. Okay, so my confidence interval would be my p hat plus or minus my 0.054. Now, next question. If the scientists want to cut the margin of error in half, how many deer must they inspect? Right? So if we want to cut this in half, how is that going to affect this? Well, one way to, and I'm assuming they mean it's still a 90% confidence interval, right? One way to do this, to investigate it, is to just physically, like if we just take our number here and we just split it in half, or this number, right? And we just say, all right, let's say we want to get this, right, which is half of this. And we set that equal to all of this, and basically we set it up the same way, but I think you know what I'm going to leave as the unknown, right? The n. We want to know what n value is going to be required to wind up with this. Well, now we're solving for n. Hold on a second. I'm just going to, whoa! Okay, hold on. Okay, so here we go. Okay, so now I'm solving for n. So I have this divided by this, right? 0.027 divided by 1.65. And so I'll do a little algebra for you here. Equals the square root of da-da-da-da-da-da-da. And then I have to square both sides. And so I wind up with, now careful, the calculator gives you something in scientific notation. So you have to interpret that, see? You got to interpret that. Okay, 1, 2, 3, 4, yeah. And that's going to equal the rest of this stuff. Oy, 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 oy. Oh my God. Okay, over n. So if we multiply, so basically you can see it's going to be 0.209 times 0.791 divided by this junk is going to be the n. So we'll do that. We'll do 0.209 times 0.791 divided by 0.0002677. Okay, so n then is going to be, I'm getting 617.55. So we'd better round up. We don't want the lower number of deer here. It only makes sense to have the higher number. So we'd say we need at least 618 deer to make this work. Okay. And is that the last one? Yes. Wait, no, it's not. It says, what concerns do you have about this sample? So it's probably going to be something about independence. Okay, so at this point we could say something about how this is probably a convenience sample. These are the deer that were taken by hunters. You know, what affects that? Like, in other words, what makes a deer more likely to be taken by a hunter? And maybe that somehow is also correlated to Lyme disease. So, some type of, confounding variable, or something else about how, maybe these deer, if one had Lyme disease, maybe it was, close by another one that would also get Lyme disease. Okay. All right, so in number 31, it looks like this is going to be yet another, or not yet another, but it's going to be another problem in which we are trying to figure out what the sample size is. So we have the information here that P, it's like believed that the population proportion is 0.25. So it looks like they're giving us P here. And this is the number of adults over 50 who never graduated from high school. We want to see if the percent's the same among 25 to 30. So this is a particular P, but it looks like we're not going to know the P for what we want to know about. So it says, how many of the younger age group do we have to talk to estimate the proportion? So this is actually not the p-value that we care. It's a p-value in the problem, but it's not the one we care about. Because this is for the over 50 set. We want to know, people from 25 to 30. So the younger age group. So how many do we have to survey in order to estimate the proportion to within 6% with 90% confidence? In other words, if we do a 90% confidence interval, right, and we multiply by the standard error, how can that be 6%? So in other words, what n value do we need? Oh my goodness. What n value do we need in order to get the standard error to be such that this works out? Now this actually implies that we have a particular p hat that we're going to be dealing with. And so actually, I shouldn't have crossed out this guy right here. It looks like we're actually going to use this as our potential p hat. I mean, they didn't give us any other information about our sample that we might take or that we have taken. They didn't say we actually took a sample and got a such and such proportion in the sample. They just said it's believed, that it's 0.25. So I mean, there's nothing you can do here other than to use this. So I shouldn't have crossed it out. So we have our critical value times the square root of. So we'll say that's what we're using as our proportion. That's the complement of the proportion. And we want to know how much is this so that we have 6%. Okay. So you're dividing by 1.65, you're squaring it, and then you're multiplying. So let's see, I'm doing 0.06 divided by 1.65. I'm squaring my result, and then I'll just write this. This is where you should be if you did what I just said. Let me try writing with my finger, maybe that'll work. It's okay. Okay. Well, that's not too bad. We'll try that. Okay. Equals 0.06. Okay, let me just shrink you guys down here. Okay. So then that means 0.06n equals 0.25 times 0.75. Okay, hang on. We'll make it look... Okay, so that's a little better. So now I just do 0.25 times 0.75 and I divide by... oh, hold up, I'm sorry. No. I squared this. I squared it. It's not... No, it's not 0.06. Hang on. Okay, so that's what you should have seen. All right. So what we really have then is 0.00132 divided by the product of 0.25 and 0.75, And so you wind up with n, oh my God, I did that wrong. 0.25 times 0.75 divided by 0.00132. I'm not writing out the math, that's why I'm screwing it up. So the number of, what are we even talking about? Number 31, we're talking about adults. Okay, no, ages 25 to 30. This is how many apparently you would need. 142.05, and that's so low. Maybe we could round down. I don't know if they're going to let us, but I would say 142. Okay, then it says, suppose we want to cut the margin of error to 4%. What is the necessary sample size? So now all we have to do is change this to 4%, divide that by 1.65, square that, and we wind up with something that, you know, it's going to be in the calculator, it's in scientific notation, so you got to be careful, but it would be like this, approximately that. So we do 0.25 times 0.75 divided by that number, and we wind up with, if I round up, which I guess I should certainly in this case, I have 318 people that I have to poll. Okay, and then finally, what do I need for a margin of error of 3%? Well, it's the same process now, and I can erase this too, because now I'm changing it to 3% that I want. But everything else is staying the same. I still want the margin of, I still want the 90% confidence, and I still have the same other value to work with. So once again, I'm doing 0.03 divided by 1.65, I'm squaring it, and I wind up with now something even lower here, as I should expect. And when I solve that, I wind up with even more people that I have to ask. So you see, if I want a smaller margin of error, I need a bigger sample. But in reality, you know, there are problems with bigger and bigger samples. I mean, you can imagine. It makes the study less realistic to, you know, actually conduct. But anyway, there's your answer. So that's number 31. And you know what? Maybe we should round this one up. I don't know if I would really get away with rounding that first one down. It was just so close. But this one has 568.18. So I'd better round it up to that next person. Okay. I think we have one more to do, number 35. So, pilot study. State's environmental agency worries many cars may be violating clean air emission standards. The agency hopes to check a sample of vehicles in order to estimate that percentage with a margin of error of 3% and 90% confidence. 90% confidence times a standard error equals 3%. Okay. Gauge the size of the problem. To gauge this, the agency first picks 60 cars and finds 9 with faulty emission systems. Okay, so we have a p-hat value. We have a sample of 60, right? And we got 9. So we got something to work with. That's a small sample. We got a p-hat value of, that's 15%. Okay, so they're saying, okay, now hold on one second. Okay, so they're saying that in order to figure out how to get this particular standard error, to get this margin of error, they tested the waters here. They took a sample of only 60. They got this. Now, since this is, their 90% confidence interval is actually going to be pretty big around that. It's probably going to be bigger than 3% because they only used 60. So we want to know how many people should they go for now if we assume that, if we use our 0.15 as our p, which is like the best we can do. It's the only information we have. So we have 0.15 times 0.85 and so on. So I'm going to do 0.03 divided by 1.65. I'm going to square it, and I'm going to get 0.15 times 0.85 over n equals 0.00033, and I'll round up to 1 there. Okay, so solving that out, I have 0.15 times 0.85 divided by 0.000331. And n, it looks like, is going to be, and I'll round up to be safe, 386. Okay, so that's how many should be sampled for a full investigation to get the margin of error of only 3%.